Okay, so this time I want to do a video which is accessible to beginners, so there aren't going to be any prerequisites. But on the other hand, I want to sort of synthesize and put together a lot of the things that I've been talking about over the last sort of half a year. So, in particular, there are sort of three or four things that I want to combine. Firstly, linear algebra and the study of two by two matrices. This is a topic which is very close to my heart. I think it's a fascinating thing to look at, although it is a bit algebraic. And I want to sort of remedy this in this video by taking a kind of graphical approach to this. So um, I'm going to be using some buzzwords now because I'm telling you what I'm going to talk about. But if any of this is unfamiliar, don't worry. The whole point of this is to introduce these concepts. But I'm going to be using something called graphical linear algebra, which basically is a kind of way that you can take linear algebra and make it visual and sort of connect it with category theory. So that's going to be the main tool that I'm going to use. And basically, it's a fairly simple idea. It's just that we have something like a signal flow graph. So we have, let's say, inputs coming in on the left, so X and Y. And then these black nodes denote copy. So here we copy the X. The X is a number. Now we have an X and an X. And the white nodes denote addition. So this would be X plus X or 2X. And then this Y gets copied. So we have a Y here and a Y here. And then at this point, we add the 2x and the y, so we get 2x plus y. So the outputs here are 2x plus y and y. And we can think about this thing as a matrix. So if you know about matrix multiplication and things, then I can say that we can have a matrix like this. And then if we apply it to an input x, y, well, then we get the correct answer. And so, really, you can think about this as basically being a sort of matrix. Instead of sending a two entry column vector to a two entry column vector, it sends a pair of inputs um, to a pair of outputs. So, that's the kind of idea. However, if you have a look at this, you may notice that there's some kind of tidying up that can be done. There's going to be other signal flow graphs that we can draw, which are going to do the same thing. So that's when we get into this kind of world of doing rewrites on these signal flow graphs. So what this basically is it's a completely graphical way to do the same stuff as we do with arithmetic. Okay, so basically there are certain rules for manipulating pictures like this, basically sort of certain equations that will hold true, mostly these ones, and we can apply those equations to change our signal flow graphs. And as we do that, we can sort of simplify them. We can simulate the effect of multiplying out matrices. We can basically do linear algebra. And this is really pleasant because, in a sense, it feels like we're getting underneath arithmetic to something more fundamental. Okay, that ultimately maybe it's these kind of shapes behind things which are really governing how linear algebra works. Maybe. But something else that's very interesting here is that we can actually be a bit more explicit about how we're applying these equations. And basically, rather than just having these sort of two-dimensional string diagrams or wiring diagrams, whatever you call them, we can instead think about a kind of three-dimensional diagram where different slices of it look like this. And as you kind of move forwards in space, the kind of slices will deform according to these kind of rules. So then we end up with a kind of surface, and we can see that that surface is kind of changing, and the way that that surface changes corresponds to a sort of simplification of some kind of a linear algebra expression. Um, and so this is also very interesting because it means that what we have a look at can be visualized in this kind of setting. So um, I believe that this is a kind of backdoor into category theory. Um, and I'm kind of going to talk about that. Like, this isn't really a category theory video, so I'm not going to be like super focused on that. But I definitely think it's really interesting that basically this kind of manifold diagram or string diagram or graphical linear algebra based approach can get us to these categorical concepts. What else? Well, like maybe the final part of this, what I want to do, which I think is cool, is to do with studying these two by two matrices. Okay, so in my recent videos on Coxeter groups, I was kind of getting to the matrix representation kind of question, which is really fascinating. Okay, Coxeter groups are really fascinating anyway, and they have a lovely way of sort of sitting in the heart of geometry, but they also have this manifestation in terms of matrices. Okay, there's a very natural way to represent these Coxeter groups using matrices, and that's kind of what I was talking about. So when we look at things that involve two by two matrices, we can kind of make this into a story, okay? And it's a very interesting story. So it's basically the story of representation theory, and we're going to have a look at the square in particular. But we're going to see how all the sort of linear algebra involving this works in a very nice coherent way. And I think the coherence is going to be kind of amplified by using these string diagrams. At least I hope so. Maybe it'll end up looking artificial, and people will prefer to rework it just using matrices. But let's see. And then finally, maybe the most special aspect of this, um, in a way, is that I'm also going to talk about two by two matrices mod 2. Okay, so this is something very, very special, which um, I've been looking at now for a couple of years, um, mostly due to the guidance of my friend Jesse Burton, who sort of pointed me at this subject to begin with, and I found it completely fascinating. But it's the question of understanding the two by two matrices mod 2. So basically, it's very simple. We just have these two by two matrices, and they can have zeros or ones in them. And we're interested in what happens when we multiply them together or add them. That's it. It's really a very simple thing to think about, but the math that comes out of it is just extraordinary. And we're going to have a look at, in particular, the sort of special linear group that appears in that kind of setting. And I'll get to that later, but hopefully you're going to enjoy that too. Okay, yeah, so the main thing that we're going to be discussing today are these diagrams, really. And what I want to do is to talk about some kind of situations that happen in linear algebra using these diagrams, because I think it makes the situations clearer, and I think the diagrams are just a nice way of looking at things. So how do we read these? Well, what I usually do is I just think of the white dot like this as meaning add. So two signals come in and we add them together. So, for example, if we have inputs X and Y coming in from the left, those would be numbers. Then once they go through that white node, they get added together. So this is X plus Y. And on the other hand, this black node means copy. So if we put an X in here, then we get an X here and an X here. And the other kind of fundamental things that we can do are basically that we can make a zero. That's what this does. And this just deletes whatever is coming in on the wire. So we just discard it basically once it flows through here and nothing comes out. And then also we can pass one wire over or through another one. Okay, so for example, here we pass this wire over like that and over like that. We're not really worried about which wire goes over which one. We're not tying up knots here. We can just sort of pass these wires through each other and then we can pull them back out, and we don't worry about things getting tangled up. If you like, we could pretend we're in 4D or something, so we don't have to worry about things getting knotted up. And so in this case here, if you just imagine sort of topologically pulling this thing tight, then you're going to end up with two wires like that. So this is basically the identity of a kind of two-dimensional space, because it takes two numbers and it doesn't really change them. And the same is true, of course, from the left. So we do have this ability to swap. I could say for people who know category theory, basically what we're working with here is a symmetric monoidal category. It's actually a symmetric monoidal category that just has a single kind of generating object that corresponds to this wire. So unlike some categories that have complicated objects, in this case, our objects are just loads of wires in parallel, and every wire is the same as every other wire. And then the other thing I wanted to say, just as a general remark, is we have these kind of laws as well. So I don't always talk about these, but these are the usual things you have in a symmetric monoidal category. So if you have some kind of gubbins here and you have a kind of swap, then you can kind of pull this gubbins up from a swap. It's kind of obvious topologically. And in a similar way, we can have a situation like this, for example, where we take just one input now, and then we're going to produce a zero, and that is an output. So this is a sort of linear map from 1D space to 2D space, if you like. And we can redraw it like this, just by moving this stuff from through the wire, if you like. So that's a very fast update to this. Now, I have a video I have a video category theory for beginners, linear algebra. And even if you don't know category theory, I think if you watch the first sort of 20 minutes of that, it also gives a good introduction to these so-called signal flow graphs. And also there's this graphical linear algebra blog. So it's just such a wonderful blog here. It has all these episodes. I especially like episode 24. So this is going beyond the system that we're talking about here, into a system that's to do with linear relations instead of vector spaces. And it's even more beautiful. It's sort of like a completion of the system that we're working in. But we don't need to go this far for the system that we're doing. I think it suffices to get up to this block number 18. But especially, well, even if you do know category theory, it's just such a good blog. At some point in the future, I'd really enjoy looking at SU2 and looking at some of these kind of matrix groups that are really significant for physics, but using this graphical linear algebra point of view. I believe that might open up some new doors. We're interested in systems where we have numbers flowing in and numbers flowing out. So two numbers come in, two numbers come out, let's say. And we have two different kinds of operations that we can do. We can copy, which sort of splits the wires, or we can add, which takes the numbers on the wires and adds them together. So if X comes in on this input, then we have X and X. And so we have 2X here. Actually, there are a couple of other operations that we have. One of them is delete, where a wire just ceases and we discard whatever input there is. And finally, we have this ability to generate a zero. And so the thing is here, we have two numbers that come in and two numbers that flow out. And so, in fact, we can represent this by a matrix. So a matrix is where we have, for us, we're just going to talk about 2 by 2 matrices. So we have these four numbers, A, B, C, D, and we put them in a square like that, and we say that's a matrix. And then a column vector is where we have two numbers, X and Y, one above the other. And that there we can think of those as two numbers, which are our inputs. And then when we multiply this column vector by this matrix, the result, let's say by definition, is AX plus BY CX plus DY. And if we have a look at this situation now on the left, and we consider the matrix 2, 0, 0, 0, well, if we apply that to the inputs X, Y, then the output here is going to be 2x, 0, according to this rule here. And you can see in this picture that the inputs are X and Y, and the outputs are 2x and 0. And so, in a sense, we can think about this part of our diagram as really corresponding to this matrix 2, 0, 0, 0. Now, if we want to be even more sort of explicit, let's say, about what this calculation is, we could even add a little bit onto the left-hand side of this. So we could say, okay, rather than annotating the flow with these sort of informal purple notation, we could actually begin this with an X, and we can begin this with a Y that we can start with. And then, when this thing reaches this point, it's going to split, and then when it reaches this point, it's going to add, and it's the usual sort of signal flow thing. But we can think about having basically graph rewrite rules or structural rewrite rules, which will take the position of what we were doing with arithmetic over here. So that's the sort of benefit of this diagrammatic language, although something a little bit awkward about the translation is basically this sort of mistake, if you like, that we write matrix multiplication the wrong way around. Okay, so what this is really saying is start with this vector here and then apply this matrix here. And that's how we see it in this picture. We read it from left to right. We start with the vector, apply the matrix. If we think about the whole composition, that equals this output here. And you could get that as a result by applying these kind of structural rewrite rules or equations to this kind of situation. And we're going to look at how that works later. Okay, so this is post-recording Richard here, and I just wanted to revise what I was talking about with this diagram a little bit. So basically, although I think the notion that we can make an X and make a Y and then pass them through the system and have some kind of rewrite rules that would allow us to record what's happening as we do that, I think that makes sense. But that's not exactly how this would work with the basic rules of graphical linear algebra. So So the long and short of it is that I should have modified the diagram basically and drawn it more like this. We start with a copy there and we have a single input. And that's basically because this kind of diagram here corresponds to a column vector like this. Um, Now, there are more sort of details that we can get into, but I think this is fine because this all fits in with the rules of graphical linear algebra. So, what I mean is that if we have a look at this page, um, I've just pasted it here, but this is from the Graphical Linear Algebra blog. You can see how this thing here, where we do the copying, corresponds to this column vector here. And I'm imagining a similar setup, but where we have these sort of scalars on the wires, um, which are multiplying these flows by x and y respectively. And so that's going to give us this column vector like this. Um, so that's fine. And then, in fact, another great work that's discussed this kind of graphical linear algebra. I mean, in the book, they refer to them as signal flow graphs. But it's this book by Fong and Spivak, Seven Sketches of Compositionality, which is a real masterpiece. And this is part of it is this theorem 5.60, which basically describes this kind of graphical linear algebra system that we've been talking about. But they have these sort of scalars in there here, and I think these can be taken from um, a more general ring, or maybe it's even a rig that's allowed. But yeah, you can have a look at that book; is very accessible. So if we adopt this convention, which makes more sense, in fact, I think the idea of pulling an X out of nowhere, although it makes sort of intuitive sense. I think there's sort of issues with how that would work with the category theory. Like it's okay to make zeros, but other things, better to think of them as flowing in from something else on the left hand side. And in fact, most of the time when we're talking about matrices, we're just going to leave the left hand side sort of open and we're going to imagine being able to plug flows in and we can just sort of ignore this and think, okay, well, what happens if we feed in an X here and a Y here? And then we can translate between matrices and diagrams. So these kind of details are not really going to um, really bother us too much in the rest of the video. Let's consider another matrix. So how about this matrix here? This is one of my favorites. So what's this matrix do to an input? X, Y. Well, to find the answer, we do this times this plus this times this, and that's what we write up here, which is Y. And similarly, we go and we find out that we should put an X there. That's this times this plus this times this. So the result here, so the result here is YX. So if we want to draw this as a wiring diagram or a string diagram, um, we want something that's going to switch over, so something like that. So this is what our matrix corresponds to. So now let's consider what happens when we compose. So let's say we want to multiply these two matrices together. So let's calculate this out. So we do this dotted with this. That's 0. We do this dotted with this. That's 0. We do this dotted with this. That's 2. And we do this dotted with this. That's 0. And when I say dotted, for example, AB dotted with A dash, B dash, A dash plus B dash. It's the Euclidean dot product of a row vector with a column vector, which gives the corresponding entry in the matrix. That's the product of these two matrices on the left. So that's what we should expect. But because of this funny convention, what this really means is that we do this matrix after we do this matrix. And so when we represent this kind of thing diagrammatically, we'll say, okay, first we want to draw the diagram for this matrix. So what's the diagram for that? We have it up here. So we have our two inputs come in. Our second input, we delete it, and then we make a 0, and that's what comes out as the second output. And then for the x, the first input, we copy it and add it to itself, so that effectively times it by 2, and that's what comes out. So this here corresponds to our matrix 2, 0, 0, 0, and that's what we do first, because remember, this notation means do this after we do this. If that if that seems a bit confusing, I'd refer you to, I'll put the timestamp on, but there's a certain point in one of my YouTube videos where I go through sort of where this formula for matrix multiplication comes from. But basically it's like in category theory and like in a lot of places where we sort of say f of x. Really, x is the thing that we start with, and then we're going to do f. So a better notation for it really is start with x, and then do f. So whereas this sort of notation, which is also written like this, has this symbol here, which means after. And so that's kind of what we have here. We can also have this, which means then. So x and then f, which agrees better with the diagrammatic notation. Anyway, let's get back to this situation. So we have this as our first matrix, and then this is our second one, which is this. So we draw that here. And now you can so this is our other matrix, our one that does a switch. And so now it's interesting because we can actually apply the kind of equations that we have for free in our graphical linear algebra. That means these equations here, and we can sort of use those to tidy up this picture. And if you're used to doing uh, if you're used to playing around with networks and doing graph theory kind of stuff, all topological things, then the natural kind of stuff that you'd want to do is what you do. So you basically you can just kind of deform this thing in the way that you'd expect. So this table here was taken from graphicallinearalgebra.net, I think is the web address, but it's Paul Sobocinski's graphical linear algebra blog, which is just amazing, which I'm basically taking a lot of this stuff from. So I hope that's okay. I've got to say that I don't think I could describe this anything like as well as he does there. Um, so, you know, that's well worth checking out. But um, the point is that we can basically get from here to here. The point is that we can basically get from here to here by applying a sort of rewrite rule or equation where we move this thing across the wire. And that's an extra rule. So I took these equations or rewrite rules from the Sobosinski blog, but I think it's earlier on maybe where he talks about this thing that we also have another rule, which is basically that you can pull the wires over or under each other. We don't even mind whether it's over or under, but you can move them through each other. So you're fine to move this zero making gizmo over this wire so that this part of the diagram here is equal to this one here. And applying that kind of thing over here um, allows us to move this thing up here. And then that means that this diagram here is equal to this one here. Um, and we can see that these two things are um, functionally the same. And what are they doing sort of functionally? Well, if we give them an input x and a y, then we're going to get a 2x and a 0 there. So that's what this ends up doing. And what kind of matrix ends up making that kind of thing happen? It's this kind of matrix here, because if we give it the inputs x and y, then we get a 0 coming out upstairs and a 2x coming out downstairs. And so this equation tells us that this sort of diagram corresponds to this sort of matrix. And that's nice because, as we've already seen, this matrix here, 0, 0, 2, 0, is equal to our J matrix after our other matrix. So basically, we can work out the matrix multiplication directly like this, or we can work it out diagrammatically like this, and we can apply these kind of structural rewrite rules that we have, and we shall go through what all of those are. And basically, what I want to talk about in this video is looking at linear algebra from this sort of graphical point of view. And I actually had in mind to study a particular example that I've been interested in for quite a long time, um, which, yeah, it has to do with some symmetries. But the thing is, I believe that using this graphical linear algebra and maybe some nice choices of subject matter to look at, we're going to get a sense of some kind of maybe some novel perspectives on some things involving linear algebra and group theory. But I think the fact that we're using this graphical linear algebra is like it brings many benefits. So one of them is that it makes the subject a lot more sort of accessible. And another is that it gives us a new kind of perspective on what's happening in these different areas. And today I'm just going to sort of take a few steps using this, but maybe in subsequent videos we can look more into different things. So I think one application, for example, is matrix powering. Okay, so what's matrix powering? Well, it's basically where you get a matrix and then you keep multiplying that matrix by itself. So, for example, we could talk about this matrix here, and we can times that matrix by itself. And the answer here is this matrix here. But now take a look at how the situation looks if we use graphical linear algebra. So we've already observed that this diagram here corresponds to this matrix 200. So if we connect that up with another copy of that diagram, well, then this is going to correspond with this matrix multiplied by itself. So, okay, here we have it. Now, how are we going to actually work out what this is? So, okay, this is what we start with then. And what we'd like to do is to use these rules of graphical linear algebra to simplify this. So what we can do is whenever we can sort of draw a region within this picture and then match this up with one of these sort of rewrite rules that we can apply, well, then we can apply that rewrite rule. And now we can continue. We can apply this rewrite here to this region here. And that lets us delete this. And now this is where I think it gets quite interesting, because we can carry on actually. I mean, at this point, you can already look at this diagram and see that it's going to end up multiplying the input by 4. But there's a bit of sort of awkwardness in this diagram. I mean, we have two wires that are crossing over each other. I mean, that's just a bit awkward. And in fact, we can get rid of that by applying these kind of equations here. So in particular, if we have a look at that region there, we see that it basically looks like this. And so we can apply this equation here. And so the way I think about this is I look at this picture here and then I think about this leg here and I imagine that um, this, if we ignore this leg for a second, pretend it's not there, imagine that this is a sort of ball and it can, or like a bead on a wire, and it can go along like that. And then imagine that this is made out of string and it's attached to this ball as this ball goes around there. And that's how you sort of form this picture here to this picture here. And in this case here, basically we're focusing on this tree structure here. And so it only has one child to the right, but the child to the left has children. So we get those. And then this node here moves along to here. So that's why when we apply this equation here, the result is this diagram here. So that may be a bit cryptic. Just keep watching if it's confusing because we'll be applying that rule other times. And I think the way I've drawn this, it's a bit difficult to see all the details. So hopefully we'll encounter some cases that are easier to visualize. Right, so here's another case that we can look at. Let's consider applying the rewrite rule here, which would be corresponding to this associativity rule here. So in terms of in terms of arithmetic, this is just saying that if we have A, B, and C, then this is B plus C, this is A plus B plus C, and you get the same answer if you add it up the other way. So it's to do with bracketing um, like that. That's why it's called the associativity. Um, but diagrammatically, it means that we can sort of slide this up to here. So we can just sort of redraw it like that. And now let's apply the associativity about here. So we have it branching out here and then branching again. So we want to move this node to here. There we are. Now let's apply the map here. Now here. Now here. And we see something really remarkable, okay? That this is 2 plus 2. And this is timesing by 4, okay? So I know all of this gubbins at the bottom always just came along for the ride. So the really interesting thing there was how this thing at the top changed as we applied these different rules. And basically, I was just applying associativity over and over again. But what we managed to get really was that the thing that was flowing along this top channel to begin with was this thing here that was multiplying by 2 and then multiplying by 2 again, right? So let's see how this works. We started out with an x, and then we have an x and an x because we copied, and then we do adding. So then we get 2x, and then we copy that, 2x, 2x, and now we end up with 4x. Now, this is, more generally, if you, for example, how would you multiply by 3? Well, what you can do is you can multiply by 2, and you can also have a third thing. Yeah, you can add these, and then you can add these. And that's going to multiply by 3. So let's see this. So x, we've got an x and an x. And here we've got 3 of them. And then we have a 2x there. And so 3x comes out. So yeah, this top thing here ends up multiplying by 4. Okay. So what do we do next? Well, okay, we tidied up the bottom bit. We sort of threw away this bone using equation B4. Um, so that's one thing. But the other thing that we did was we basically opened up this multiplication. So as someone interested in number theory, I find this really interesting because we're just multiplying together these integers, but there's a sort of behavior underneath that's happening here. So when we multiply them, we are using this equation here. And so we have this. And then we can begin to apply our associativity or this equation here. I mean, I'll just call them both associativity. And you saw how we did this until eventually we're able to transform the picture into this. So what is this? Well, our input x comes in, and then we copy it. And then this basically multiplies by 2. So we end up with a 2x here and a 2x here. And then we're adding them. So in a sense, what you can see here is a sort of visual proof that 2 times 2 is 2 plus 2. So this at the beginning here is 2 times 2. That's what this is showing you at the top. So I find it really quite interesting that now the number 4, um, because we can apply all these different rewrite rules, I think it can now be thought of as some kind of a, well, you could say that a equation that multiplies by 4, some people would say it's a quotient. Okay, they'd say there's some kind of an equivalence relation which is involving applying these equations, and you can think of it that way. But I think that um, some people are very quick to go to, a sort of classical explanation of this, but maybe we can try and look at this a bit more from first principles. I mean, I find it very interesting that just by having these equations, or there's a couple of other ones that we might want to add in there, some stuff involving if we have a -1, or maybe we're going to look at some addition modulo 2 later, which I think is going to be very interesting. But whatever we look at, um, I find it very interesting that there is this graphical way of looking at this. Okay, so the next thing we're going to look at, I think's going to involve a lot of different topics I've been discussing over the last few videos. In fact, it kind of makes me chuckle because I can think of so many different topics that are sort of going to be combined here. So in a way, we're just going to look at the square, and we're going to look at the kind of symmetries of the square and how those can be described as these maps, and how these maps can be described using graphical linear algebra. So in a way, you could say we're studying symmetries and geometry, and this falls directly under the umbrella of my perfect shapes video or other videos on Coxeter groups. So if you've watched those, you'll realize how what I'm going to talk about can be put in terms of those, although I'm not going to um, digress too much. But also the matrix approach should remind you of things from my recent video on 2 by 2 matrices, um, or Weilberger's dihedrons. And I'm going to try and combine this a bit with the graphical linear algebra and with the maybe with homotopy IO as well. So yeah, let's take a square then and ask a good question, which is, what are the symmetries of the square? And there are some symmetries we can get by rotating the square, and there are also mirror symmetries of the square. So why don't we start by drawing in the different lines of symmetry of the square? Those are lines where we could put a mirror and it would reflect the square, so things kind of look the same afterwards. So we find that there are these 4 different lines of symmetry of our square, and they kind of make this Union Jack style pattern. And what I'd like you to do is to think about these different lines I've drawn, these 1, 2, 3, 4 different lines I've drawn as mirrors. In fact, if you just think of the purple 2 lines as mirrors, um, then you'll have a sort of kaleidoscope, and you have this sort of region here that we sometimes call the fundamental region. And if you imagine putting something inside of this, some kind of an object that you wanted to look at, like a little square or something, then you can look at the images of this in these different mirrors. And in fact, we're going to have mirrors reflecting in mirrors, which make virtual mirrors. So we could think of these blue lines as corresponding to virtual mirrors. And basically, this is a way of organizing the different symmetries of the square. So let's go to this picture now. So we have the most basic symmetry of the square, the identity map, the thing that doesn't change anything. And now in this region here, we can draw, because, if we actually have a kaleidoscope with these mirrors, as I'm showing here, and we actually put a square into this, let's say with colored vertices or something. It doesn't matter how they color them. We don't need any matching up, but it'll be physically true that the image of this within this mirror is going to look like it's had some of its colors swapped around. So we really can get a nice visualization of the sort of symmetry transforms that are being applied by these mirrors. But I prefer, because it's faster, just to write it like this, that this is the identity and this is a square that's had its diagonals flipped over. However, this actual mirror really achieves the goal of this. And it's also a good idea to think about this kind of thing as a linear transformation. And so we can literally think of this as a linear transformation from the plane to itself that just reflects everything in this mirror here. And then we want to associate that with a matrix. So in general, how do we do that kind of thing? Well, we say, okay, we have these 2 basis vectors, 1, 0 and 0, 1. And then we look at how those get mapped under our symmetry transform, and they get swapped around actually. And then we write the images of this and this as the first and second columns, respectively, of our matrix. So the first column of our matrix is the image of this vector here, which is this vector here. That's why that's 0, 1. And similarly, this is 1, 0, because 1, 0 is the image of this vector here. So that's the reason why this matrix here that applies this diagonal reflection is this basically kind of looks like the complement of the identity matrix. And this is what Norman Wildberger calls J with respect to his dihedrons. So I used a slightly different convention than Wildberger for the dihedrons. They are consistent, but just different conventions. So I'll talk about my dihedrons as I described in the last video on the 2x2 matrices. I'll put a link to it in the description. But yeah, so this is an important matrix that we call J. And then the other fundamental operation is going to be reflecting in this vertical line here. So when we do that, that's going to change our square like this. So it's basically, we're reflecting in the vertical line. And so it's this sort of horizontal reflection, interchanging the left-hand side and the right-hand side. And what kind of matrix would perform such an operation? Well, I claim that this is the sort of matrix that it corresponds with. And if we think about how this matrix works on an input, x, y, well, the output is going to be minus x, y. So if we have a vector like this, let's say, then we're going to leave the y coordinate alone, but times the x coordinate by -1. That's the same as interchanging the left and the right hand side. So there we have it. So what I'm trying to do here is, with these little pictograms, indicate the sort of symmetry of the square that corresponds to this region. But I'm also outside drawing the actual matrix. So this matrix is called J. And actually, this matrix here is called K. So this is another one of these dihedrons. So if you've watched the first part of my video on perfect shapes or Coxeter groups, I can just sort of label some points of this like this, O0, O1, O2, and that might remind you of some of that construction, but I'm not going to go into that. So if you haven't seen those videos, don't worry about it. What we're going to do basically is think about these two sort of purple lines here as mirrors, and then we're going to fill out all of the chambers here of this sort of kaleidoscope. So, okay, so we want to keep filling out this picture and find more of the symmetries of the square. So what we're going to do now is use this purple mirror here and apply it to the stuff that's in this region here. So that's going to give us something down here. So what do we write down here? Well, it's going to be the result of performing this diagonal reflection on the thing we get after we do this reflection in a vertical line. So what's the net effect of this? Well, if we start here, then first we're going to move here, and then this won't change. So that's like that. If we start here, then first we're going to move over here, and then we're going to move up here. That's going to look like this. And so the net effect here is that this is going to be a sort of rotation here. And we can also compute what matrix this corresponds to. So basically what we're saying here is that, this is this after this. So it's this matrix J after this matrix K. And computing this, that's 0, that's 1, that's -1, that's 0. So yes, this matrix multiplication here gives this, which corresponds to this. So what goes over here? Well, it's the result of doing this symmetry K on what goes here. So it looks like this. And we can see that it's this. So how do we see it? Well, if we start here, then we go along here, and then we go up here. So the net effect is to go up there. If we start here, first we do this. That doesn't change anything. Then we do this. That moves us over here. So you can see what's happening. And so this is this symmetry here. What about the matrix math? Well, it's this left-right flip after this diagonal flip. And the matrix for the left-right flip is -1, 0, 0, 1. And the matrix for the diagonal flip is 0, 1, 1, 0. And so now let's compose these together. So chop, chop, that's 0. And so that's 0, -1, 1, 0. Well, that's actually what we call I. Okay. So we can think of that as the square root of -1, or a better way to say it is that here I, J, and K form the dihedrons. So those together with the identity, if we use these four matrices, then we can take linear combinations of those four matrices and we can get any matrix we like that way. So that's one beautiful thing about these dihedrons, but there's many others. For example, um, I times I is minus the identity matrix. J times J is the identity matrix. K times K is the identity matrix. And there are other nice properties of these things, like you can multiply one by another to get the third non-identity of these I, J, and K up to a minus sign. And so somewhat similar to quaternions in a way, but it's different. Anyway, let's carry on. So next, let's apply this diagonal symmetry to this I here. So what are we going to get? Well, it's the result of applying this diagonal symmetry to here. So I think this ends up resulting in this up-down flip. So there's an up-down flip there. Now, what's it correspond to in terms of matrices? Well, it's going to be this J matrix here times this matrix I. Sorry, this is the J matrix. So yeah, that's our vertical flip. So yeah, that's our up-down flip. If we then also apply a left-right flip, then we get this very disorienting situation where everything's been moved around. So that's rotating a square by half a turn. And so if we rotate anything by half a turn, so we have like X, Y, then I think that's going to give us minus x minus y. And then finally, we can get something over here by applying this left-right symmetry, that's this one here, to this thing over here. So we've got this. And so if we start here, then we're going to stay in the same place. If we start here, we're going to move down here. So this is our missing diagonal flip. So to get the matrix for this, we need to multiply the matrices for these two together. So the matrix for this left-right switch, that's K, that's up here. And the matrix for this quarter turn clockwise, that's down here. So we need to multiply these two together. So let's do that. And so what we end up getting here is minus J, basically. So this is the matrix corresponding to this. So yeah, this is the matrix corresponding with this final segment. So the point here is that what we have is the 8 different symmetries of the square, and each of them now comes with this sort of matrix which applies the appropriate symmetry of the square. So if we consider the square having vertices at coordinates 1, 1, 1, minus 1, minus 1, minus 1, minus 1, 1, then basically we have these different sort of representations for our symmetries. So it's all very pleasant. But what I'd like to do now is to look at the same situation, but rather than doing all that matrix multiplication, let's look at the same situation using graphical in your algebra. Like I just want to show what it looks like basically. And then after that, we're going to move on to a different, a slightly different system, which I think is also even more pleasant in a way, and especially with the graphical linear algebra. Okay, so that's all the computation done. All that remains is to visualize this using graphical linear algebra. And this is really nice and easy. So to begin with, in this sort of fundamental region at the top right here, we have this identity map, and we know that the matrix for this is here, and it's going to correspond to this kind of diagram here, because we're just going to take our inputs x, y, and return outputs x and y. So we're not doing anything. We can see that that's indeed the effect of applying this identity matrix to a column vector xy. It just results in an output which is the same column vector xy. So our next objective is to calculate the diagram corresponding to this matrix J here. So let's do this in a more mechanical fashion. So let's multiply this matrix J that we're interested in by this general column vector xy. Let's inspect what the output is. It's going to be yx. So we want some diagram that's going to transform x and y into y and x. And so if we just cross these wires over, that'll have that effect. So that's the wiring diagram. So that's the diagram. That's the diagram for here. I should say, I think I've been a bit lapsadaisical in my usage of the terms string diagram and wiring diagram. I think if I'm being precise, I should call these things string diagrams, and reserve the term wiring diagram for something to do with vibrations and lenses and things. which and open dynamical systems, which is not what I'm discussing here. However, you know, there is some flip-flopping in terminology here between calling these things string diagrams and wiring diagrams and graphical linear algebra and pictures of matrices. So I'm just going to use all of those terms kind of interchangeably. Um, okay, so the next one then is this matrix over here, K. So what is going to be the string diagram corresponding to that? So if we apply it to an input x, y, we get an output of minus x, y. So we can take in our wire, our x wire, and then we multiply it by minus 1. We denote that by drawing a box on the wire. And then we'll leave the y wire alone. So that's going to be the diagram that corresponds to K. So what we're seeing here is that x and y come in, and then minus x, y come out. And so this is like multiplying by minus 1. So this is sometimes called an antipode. Now we need the antipode for the square because these matrices involve minus 1. And so the rule set is extended here. So these are the rules we've already seen. And now we have these additional rules involving this antipode. And we'll talk about those later as we apply them, right? Because now basically the kind of matrix math that we did to get all of this stuff, we can now do diagrammatically. So how does this go? Well, let's talk about one of the regions we don't have a diagram for yet. How about this one? So so this one here, so this one here is the result of doing this diagonal flip operation when we start with this sort of left-right flip here. So that's why we can write this sort of rotation here as this diagonal flip after this left-right flip. Now, in terms of matrices, here's the matrix for the diagonal flip, and here's the matrix for the left-right flip. But now we want to write this in terms of wiring diagrams. So in terms of matrices, it's this matrix after this matrix. But remember, we build our diagrams the other way around. So first we want to write our diagram for this matrix here. So what's that going to be? Well, we've got it over here. So let's copy that down. This is our first part. It's this matrix here. And let's just make a note what this is. This is this matrix K here. All right. Now the next bit. So this corresponds to this. And remember this notation here that we want to unpack is this after this. So the next thing we do is for this. So what is this? Well, it's here. So it corresponds to this thing where we twist our wires over each other. Pass our strings over each other. So like that. They go through each other. We don't mind about which one goes over the top of which one. So we have this here. And so we have this part here, which is basically J. So there we have it. And does this have the correct behavior? Well, if we supply it with xy, then we're going to get minus x is going to come out here, and y is going to come out here. So does that correspond to what this matrix does? Well, let's check that out. So there's the matrix. Let's give it an input x, y. And then the output is going to be y minus x. Yes, so that works. So that's how we compute the diagram corresponding to this. I mean, ultimately, it's often nicer just to work within the graphical framework directly, but it's totally possible to go between the two regimes. So let's carry on computing then. What about this one over here? So this is a sort of similar story. We want to do this left-right flip. We want to do this left-right flip after this J. Okay, so in terms of the diagrams, we want to be drawing it the other way around. So first we do J, and then we do K. That's what it is. And so let's test how that works. If we supply it with an input, X and Y, then we get minus YX. Does that agree with how this matrix I works? Minus Y X. Yeah. Okay, we could carry on. Okay, we can carry on computing. But I mean, I know that this is minus the identity matrix, so you can just do this. And then if we do a twist after this, that corresponds to reflecting in this mirror. I think that's completing the picture. Oh, hang on. There's also this one. So this one corresponds to this matrix here. So it's going to leave X alone and it's going to multiply Y by minus one. So yeah, there's also a sort of symmetry in this picture now. If we sort of look at opposites, they have a kind of pleasant, I suppose, it's timesing by this, I suppose, as part of the symmetry of it. So that's all very nice. Now, I think there's a lot of places to go with this. When I was looking at this, I was thinking, well, around these nice things in representation theory now, we get all these manifold diagrams. And what about if we had ways of um, having some sort of physics deciding which of the different equalities or transitions or rewrites one performs? It seems to lead to some quite interesting um, possible structures. And it gets nicer perhaps as one follows more of the graphical linear algebra blog, going into LinRel where one introduces extra structure, sort of co-addition and co-copying to make the thing fully symmetric. But the system that we've been working with is still pretty simple. Um, with these sorts of rules. Um, and we can use it for the graphical in your algebra. And I mean, in terms of category theory, we're also dealing with something that's quite, um, it's quite a sort of commonly occurring structure, which is a category with byproducts. So I'll see if I can link a chapter in so I'll see if I can link to a chapter in Lebere's book, which gives a really nice explanation for the connection here with byproducts. But I don't want to get into that kind of category theory directly in this video. I want to talk about all of this from a more sort of intuitive point of view. And I think that it's pretty nice is being able to look at what's going on with the square in terms of these sort of diagrams. Also because it can be combined with homotopy IO, which is some really interesting software. Um, so, hmm, yeah, I think I'm going to say something about that. Um, and then I want to get on to talking about these matrices. So these matrices mod 2. So that's something I've been sort of working up to. I'm excited about discussing that. But um, I think this is an interesting sort of question to think about. So for this, we're not going to need the antipode. Okay. So the antipode is basically times two by -1. Um, so suppose we just want to take an input and multiply it by 3. It's a fairly straightforward thing we might want to do. Um, now, the thing is, we can take this picture and we can apply a associativity equation. We can apply this equation here to rewrite at that point. And so here's another, how do we do this? Well, the way I like to do it is I draw a rectangle around the part that I want to operate on because everything outside of that rectangle's not going to be changed. And now I imagine this point here sort of sliding along here to go to here. And then I redraw as I imagine that. So now this just connects all the way up here. And we still have this wire going on here, but now it has this junction slid down to there. And that junction used to be connected to this thing here. And now we're just drawing what's outside of a box. So that's sort of one thing that we could do, if you like, from here. We could apply that particular rewrite rule. There's another thing we could do would be to do the same kind of thing here. So I'll just do that. You might want to pause the video and give this a go. Okay, and then another thing. So that's sort of the result of operating it that way. And then also, if we take this diagram and we apply the associative rule here, then we can redraw the picture like this. And so actually, we find that there are these sort of four different forms of multiplying by the number three. And you can see that any of them work. Okay, so let's see that this one works. So x comes in, and then we have 2x is like this. So that's going to be 2x, and that's going to be 3x. And this one's fine too. So each of them work, but there just happen to be these four different forms. And it gets more complicated as you look at the case for larger numbers. So timesing by four's already a very interesting case. Um, but another remarkable thing about this is that in a sense, what we're looking at here with these pictures are sort of slices of something that's high dimensional. Okay, so in a sense, this kind of equational theory or rewrite theory can be viewed as us looking at these sort of slices of something that's high dimensional. I'll go there on Google. So, would you like to be redirected to beta? I'm going to press cancel. So now I've got to the old style homotopy IO, which um, I'm more used to. Okay, so I've loaded up homotopy IO. This is the old style version of it, which I'm more used to. And so let's make this structure. So I'm going to start by pressing plus and making a zero cell here, this red one. Now I'm going to click on this. And now I want to have this as my source. And then I'm going to click on it again. And I'm going to have it as my target. And now I have this cell 2 here. So I'm going to click on the pictogram for that. So what I want to do now is to make something that's going to copy. So I'm going to think of this orange dot here. I'm basically going to pull it downwards so it looks like a wire. These wires are going to be flowing. I think they flow from bottom to top in homotopy IO. We'll see that in a moment. But I want something that basically looks like copy. So it starts with a single wire or a single dot, and then it makes two. So the source of copy should be a single dot. So I'm going to have that as my source. Now I'm going to click on the pictogram for cell 2 again. And on this red line here, I'm going to click in the middle of this red, and that's going to make another orange spot here on this wire. There we are. And I want that to be my target. And so now we have this, which should be read from bottom to top, and it's called copy. So this purple dot here is called copy. Let me click on the pictogram from it. You see, it takes one of these orange things at the bottom, and then we do this thing called copy, and then we have these two orange things coming out at the top. So the zero-dimensional cells are just dots. The one-dimensional cells are lines, and the two-dimensional cells are these planes. But you can see that by slicing this plane at any horizontal line, we get a picture that looks like the ones we were looking at earlier. So yeah, let's just carry on. So let's clear this. Click clear. Now, the next thing we want to do is make something that does adding. So we go back to our cell here. I'm going to call this spot. I'm not going to call it cell 2. Let's call it spot. Okay, so we go back to our spot, and then we want to do adding. So we want to start with 2 spots. That's going to be our source, and then our target is going to be 1 spot. And so we have this thing here. This is called add. We read it from bottom to top. So, excuse me, that's not what I meant to do. Yeah, we read this from bottom to top. So the 2 inputs, X and Y, come in, and X plus Y comes out at the top. So it's just the same as I've been talking about in my video, except a different reading convention. So let's think about these kind of laws. And we want to have some kind of rewrites that we can use in our system that can apply these kind of rules. So let's have a look at the associative law for adding. Okay, so we can change this a little bit, put another add on there. So in this case, we're doing A plus B plus C, and we want to say that that's equal to A plus B plus C. So we want to now make a 3-cell that has this as its source. So we're going to click this as our source. And now we need to make our target. So it's the same thing. We click on add, except now we want to branch off on the left-hand side and have this as our target. And so now we have this 3-cell that we call add assoc. It's the associativity of addition. And we can make a 3-dimensional picture of it like so. It's quite pretty. Now, if you imagine pushing this into a meat slicer, then the first part that you slice off would correspond to the source of this, or one side of the equality, and the last part that you slice off corresponds to the other side. So we can see this better if we have a look at this and we see, okay, the source slice looks like this, and the target slice looks like this. But if we have a look at it in 3D and we align it like so, we can see that these slices are just the things that are in the front and the back of this 3-dimensional picture. And so if we go back to this and we have a look at this in 2 dimensions, well, what we can now do is something like this. We click down here and we're going to include a copy. And now we're going to click down here and we're going to include another copy. And so now, if you have a look at this picture, it may remind you of and so now we can see that this picture here is basically the same as this picture here, which is one of our 4 manifestations of this thing that does multiplication. However, now we've wrapped this in an associative rule. So actually what we're looking at here is the front slice. Let's have a look at it in 3D. We're looking at the front slice of this thing. And the back slice of it, you can turn it around and see what it looks like. But better to look at it properly. So we go back to the 2D case. The back slice or the target slice looks like this. So what we've done is got rid of that bubble and ended up with the thing like that. So, but you can see sort of visually in homotopy IO that it's quite, you can see in homotopy IO, it's quite sort of visually striking how we are changing one thing into another. And you can also see that maybe we could think about this thing in a sort of continuous way, and that makes more sense in some regards. And it's interesting to, well, I think it's interesting from many points of view, like that there's this connection with the geometry here, that there's connections with a sort of number theory and linear algebra. Um, so yeah, but also, I mean, if this kind of thing makes sense to you, um, if you watch the homotopy IO video and then you have a look at John Byers' videos on the periodic table of n categories, I think it's called, something like that. Um, you know, the potential for this higher category theory in combination with visualization tools like homotopy IO, the potential of that stuff to sort of transform communication, I think is huge. Um, and I wish I knew more differential geometry and things, but um, maybe there are other people that can help. But there definitely is a feel to something about homotopy IO where it feels as though there's a sort of more continuous, more user-friendly, more kind of topological or um, you know, minimum energy surfaces or something along those kind of lines. That there's more interface tools along those directions that we haven't got used to yet. So, I mean, I'm not sure if it's possible, but I wonder if, you could have something like a load of blue tack that you could make your own surface with and then be like, okay, I suppose you could always have a computer that could then scan it and turn it into something in homotopy IO. But, or maybe there's some other way that we could create these things. Um, but I think that it could be a really fast and good language tool. Now, when looking at things like these matrices, it seems to sort of cap out at 3 dimensions at a lot of it. But there's plenty there to explore anyhow. I suppose that we can look at higher dimensional um, transformations between these things. But it's also very possible to look at high dimensional categorical situations, or I mean, really, the linear algebra situation does indeed have um, a circle times in it, which I suppose should be incorporated into this. Um, that makes the dimensions and things much more complicated, but um, it's very interesting to study. But I've sort of tried not to turn this into a springboard video for categories, but basically, um, a monoidal category is the same thing as a bi-category with one object. Pretty much, you can think of it as a two category with one object. Okay. Let me get this right. So, a monoid corresponds to a category of one object. A monoidal category corresponds to a basically a two category of one object or a bi-category of one object. Let's say a two category of one object. Now, we work with these manifold diagrams, which are basically um, nice geometric models that can correspond to things in higher category theory. So when we're working with the monoidal category, essentially it's like we're working with a two category. So it's like we're working with these two-dimensional manifold diagrams, and that's what the add and the copy morphisms are. The background corresponds to the object, but the background is pure colored because like it's a single object two category that we're working with. Um, but then we want to represent the equations that we're using explicitly, and that's why we have this associative rule. And then we end up working with a three category because we have these high dimensional cells which are giving us equations between parallel things. But we visualize those using the sort of um, these cells. And so when we go to this picture here, the basically the way these manifold diagrams work is that whenever we go to the next dimension, we get a sort of hypercube, and the front and back boundaries of that correspond to the source and the target. And then we'll have a sort of point in that. And then we have this sort of two-sided cone, basically. And that's like our cell that converts our back to our front. But in this case, you can see a lot of the structure is unchanged. So it's sort of like for people who have seen it, it's a bit like horizontal composition of um, natural transformations. It's that kind of idea that, we can sort of stitch together identity on part of the diagram and this associative law, which is operating on the addition here. So looking at it slice by slice, I find is the easiest way to. So what's going on in the picture? Well, the input comes in, we copy it, and then we copy this. And basically, this whole loop, if you just imagine the whole thing operating at once, it's multiplied by 2. So the input comes in, x, and then 2x, x, and then we add them together. That's this slice. And then this is where we're applying our cell. And beyond it, it looks like this. So now we're doing the adding the other way around. But yeah, I'm actually pretty interested in understanding this from a sort of geometric point of view. And also, when we look at this in terms of going further along with graphical linear algebra, we can look at this in terms of lin-rel. So this seems to be a interesting way to extend a lot of things that are dealt with in terms of linear algebra, and also looks like it could give a more natural theory of fractions, perhaps. Okay, so for the final bits, what we want to do now is to look at something simple. Okay, so um, these are all of the rules in addition to the kind of basic things involving using swapping of wires and stuff like that. These are our basic rules for this graphical linear algebra. But normally we'd be thinking about having, say, integer values flowing along the wires. That's basically what we've been talking about today. I haven't been big on having multipliers or fractions or, yeah, we had -1 at some point, but that was about it. And I want to continue being simple like that. I want to be even simpler. So let's work with integers modulo 2. So what does that mean? It means that rather than having numbers 0, 1, 2, so on, we're just going to have 0 and 1. And our laws of the of arithmetic are like this. Our laws of arithmetic are that um, adding 1 to 0 or 0 to 0 works like usual, but we also have that 1 plus 1 equals 0. That's where the modulo 2 arithmetic comes in. So basically, we just do ordinary arithmetic, but at the end we say if the answer's even, we'll call it 0. If the answer's odd, we'll call it 1. And so in terms of the graphical linear algebra, there's a couple of ways we could think of this. One of them is to say that -1 is the same thing as 1 because they are both the same modulo 2. They're both odd numbers, so we can't distinguish between them. So we could say that the antipode is the same thing as the identity. So in terms of these things, this would be adding another equation, which is to say that this little antipode thing here is just the same thing as a plain wire. But you can see that that's going to induce a lot of simplifications. And one of the kind of consequences of that rule is going to be that if we have a wire and we copy it, and then we add those two things together, well, that's going to be equal to this, the same thing as deleting the input and making a 0. And you can see that as a consequence of this law with the antipode being equated with a plain wire. That's probably the most principled way to do it. I just think of it that if you have x, then this is 2x, but you're working modulo 2, so 2 is 0. So this is the same thing as 0. So that's the kind of scenario that we're interested in working in. And if we do work in that scenario, basically, it's very pleasant. We can say, okay, well, what are the different matrices? So we're interested in 2 by 2 matrices. And when we're working over the integers modulo 2, so sometimes we could say we're working over this finite field with 2 elements, F2, or sometimes called Z2, the integers modulo 2. But anyway, there's only going to be 16 different 2 by 2 matrices, and we can write them all out. So it's just like writing out all the different binary strings, but we're putting them in these square grids. And so we can write them all out and we can work out what multiplied by what equals what. Now that might sound like something that's not fun. It's very, very fun. If you have a look at that, it's maybe one of the most profound math exercises that I ever did. And it was recommended to me by my friend Jesse Burton. And I recommend it to anyone to have a look at this. You know, it's fun to look at it for yourself as well, not just to sort of read theorems in a abstract algebra book, although that's also a good way to explore this kind of thing. Anyway, one of the things that one discovers in doing things like this is what I'm talking about here, and this is kind of the note I wanted to end on because it's very interesting. Okay, so what have we got here? Well, if you've watched my videos on Coxeter groups, or you think about what we just did with the square, and I say, okay, I want these two to be thought of as mirrors, and I say, okay, I want these two to be thought of as mirrors. This mirror corresponds to this symmetry here, and this mirror corresponds to this symmetry here, and we're talking about finding the different 6 symmetries of the equilateral triangle. And then we say, okay, Um, and so if I say all that and you've watched, say, my video on perfect shapes or whatever, then you'll probably be into this kind of thinking about drawing the symmetries and thinking about representations and maybe thinking about Coxeter groups. So yes, those are the kind of connections I want to establish. But there's a difference here, which is that we're working with the integers modulo 2. So the way that that whole picture I just described ties in with matrix representations works just as before, but the difference is that we're working with integers modulo 2. So for a reason that I'm not really going to justify, I'd like you to associate this symmetry here of the triangle with this matrix here, and similarly this symmetry here with this matrix here. Now, these two symmetries basically correspond to reflecting in these two mirrors I've drawn in purple, and we're going to see what happens to this fundamental region when we do this. Now, let's take a look at this thing at the top right here. We have this matrix drawn in green, and this corresponds to reflecting in, as is shown with this icon here. And I claim that it also corresponds to applying this kind of diagram here. So let's see what this diagram does. So we start off with our inputs, x and y, and then we have y, y, and then x plus y, and y is the output. So is that the same as what this matrix does? Let's check. So yeah, those are consistent. And let's check with this bottom case as well. Does this correspond with this matrix here? So in this bottom case, again, what we want is that this icon here stands for this matrix here. And we hope that this also corresponds with this diagram. Let's check that. So yeah, that's going to be x plus y. That's good. Okay, so now we can just proceed pretty much the same way as we did for the square. We have these two purple mirrors and we can keep applying them. So first, let's try and get what should be in this region here. Or we can do that by applying this reflection here to this here. And so we have this after this. We can draw it as this after this. And we can work out what this thing is. So firstly, let me work this out with matrices. So we have this dotted with this. That's interesting. That's 1 plus 1, which is 0, because it's 1 times 1 plus 1 times 1, which is 1 plus 1. But because we're working modulo 2, that's 0. And then that's 1 there, 1. And then that dotted with that is again 1. So we have this matrix here. Now, because of this sort of representation thing that I want to roll with, which you don't really have to believe. I haven't really given you any evidence. Just because I say a matrix should correspond to a certain permutation of a triangle, doesn't mean that everything's going to sync up. Now, I claim that it will sync up, but this is something that we have to observe, not assume. So let's just keep calculating. If the diagrammatic language does hold correct and compose these two permutations here, then we can compute the result. So we start off here, and then we apply this. That doesn't do anything. And then we apply this. That moves us up to here in the end. So we go like this, and I know that composing two reflections gives a rotation. So we have that. And on the other hand, what we can write down here is going to be this, because it's the result of applying this reflection here, which is here, to this region here, which is here. And if we work that out, that's the rotation in the other direction. And I think we can say it corresponds to this matrix by symmetry. And so now finally, what do we put here? Maybe you want to pause the video and take a look. I mean, this is going to start getting, yeah. When we start looking at this diagrammatically, yeah, I think it's like this is access to stuff that um I'm not sure people have looked at before in this kind of way. And I think there's some very interesting structures here. Anyhow, um, the next thing here is we can apply this symmetry to this permutation here. So what's the effect of this? Well, first we do this, and then we do this. So we start here, we move to here, and then this doesn't move us. So I think, yeah, the result is going to be this missing reflection here. But let's calculate this using the matrices now. So we want this vector dotted with this vector. That's going to be 0 because we're working mod 2. Next, this vector dotted with this vector. That's going to be 1. This dotted with this. That's 1. And this dotted with this. That's 0. So we've got J. That's interesting. I'm not sure everyone would have expected that. So, okay. Now what we can do is we can actually draw the pictures for these things. So I know what J looks like. Um, that's that wiring diagram there. What about this diagram here? Well, we know it's the composition of these two. Okay. So we want to draw the diagrams for these. Um, we need to sort of draw them the other way around. So first we draw the diagram for this, which is here. Let's draw that. And now we draw the diagram for this, which is here. And so we have this, and then we can apply our rules to simplify that kind of thing. So, I mean, honestly, yeah, it's difficult to um convey how much fun I think can be had with this kind of stuff. Just for example, okay, um, can this be simplified if we apply some of the rules? Or, this seems to correspond to a reflection. Does it actually have the property that if we compose this with itself, we get the identity? Well, and there's a lot more going on in this picture as we go around. So, in particular, this is well worth thinking about and how we could simplify this picture here. But then we can also always think about these things as signal flow graphs where we're doing our arithmetic modulo too. So I think there's just so many different directions that one can go using this graphical linear algebra and this kind of approach. So um, all of the stuff with the Coxeter groups can be kind of investigated with this. And when we get into the sort of the props and the symmetric monoidal categories, you might want to compare a lot of what I've said here with cooking with symmetric monoidal categories, I think it's called, um, and also my video on homotopy IO with Joss Huber. So, I think there's a lot of tools here that we can bring together. And yeah, I also think following the graphical linear algebra further and combining it with some of these sort of classical questions involving representations of Coxeter groups and all that kind of stuff. But then going a bit further and going into Linrel and looking at these nice connections with fractions and um, you know, potentially exploring finite fields and all sorts of, there's a lot of, I think, low hanging fruits in terms of the kind of visualizations and connections with geometry that we have here. Or perhaps it's just me who's wandering into areas which are um, well known and sort of, you know, um, but anyway, nevertheless, I think there's some really interesting potential exploration to be done around these subjects. So, I mean, the reason I'm talking about the Mod 2 edition here and this connection with S3 and all this kind of stuff is because there's some really great fun to be had by looking at this kind of algebra using this kind of graphical approach. So, for example, we've talked about this region down here and this matrix here. And we've seen how it was obtained by composing these things here. And we've talked about how we can write this as a diagram as shown here. Um, but have we haven't really gone into detail about how this corresponds with this matrix. And another very interesting thing is that is it possible for us to simplify this picture? So if you want a really interesting thing to think about, look at this graphical linear algebra using the equations I was talking about before. I'll show you them again momentarily. And think about how you could simplify this kind of diagram just by applying the equations of graphical linear algebra. So I'm just going to go into an example with this, but um, you can see that if you're looking at these 2 by 2 matrices with this mod 2 addition, there's a huge landscape of happenings that can be described, things involving matrix multiplication and matrix addition that can be described in terms of this linear algebra. And the whole of the way that things can change and so on is all automatically encoded by those rules. So this is, I think it's a this looking at graphical linear algebra working with finite fields and different um, things. To me, I find it to be a very exciting, um, what I view as a frontier, but I'm not an expert in a lot of these areas of abstract algebra. And, I wouldn't want to tell people to spend their time looking into such things on my recommendation. But for me, I intend to spend a lot more effort looking at finite fields in terms of graphical linear algebra and also with this category of linear relations. Because I think, for example, looking at, um, yeah, yeah. Anyway, let's go into this. So, what we're going to do is understand how this can be reduced. So, the rules of the game are shown here. These are the equations of graphical linear algebra, together with the sort of things about how to deal with wires crossing over each other, which is kind of topologically evident, self-evident. Um, so basically, we're starting with this picture here. Now I've drawn numbers on the wires just to show you that this diagram here is working as it should. But there's an interesting kind of detail here, which is that we're actually relying on the fact that 2 equals 0 because we're working with mod 2 arithmetic. Remember, we only really have 0 and 1. And if a number is even, we call it 0. And if it's odd, we call it 1. So that allows us to get rid of these y's. And so only an x comes out of the bottom. And so um, doing this diagram on xy is like multiplying this column vector xy by this matrix here in the sense that it's producing output x plus y x. Now, what we can do is take this diagram, and we've redrawn it here. Don't worry about the green rectangle for now. But basically, what we're doing now is we're just applying different equations from inside this blue rectangle here um, to reduce this original picture. And we end up reducing it down to this form here. And an interesting thing that's happened here is that we've got rid of the 2 equals 0 step. Okay, so there was basically a step in this over here where we applied this rule, which basically says 2 equals 0. Or, multiplying by 2 is the same thing as multiplying by 0. Okay, because if you think about, like, haven't talked very much about justifying these different equations. Let me just talk about this briefly. But this one here is, this is our weird one, but it's basically saying, well, this is doing x plus x, which is 2x, but 2 equals 0. So this is 0, or 0x. So it's multiplying by 0, which is what this does. Because if you want to multiply a number by 0, you can just discard that number and produce a 0. And that's what's happening here. That's acting as the scalar 0. Okay, what about these other laws? How are these justified? So this one here is saying that if we have x and y, then here we're going to have y and x. Here we're going to get y plus x. But it's saying that that's the same thing as x plus y. So that's the commutativity of addition. This one here is saying if you have an x, a y, and a z, but here you have y plus z, here you have x plus open bracket, y plus z, close bracket, On the other hand, here we have these, and then this is x plus y. And so this is x plus y in brackets plus z. And the claim is that these are equal, or these should be considered equal, as in addition is an associative operation. This is x plus y on both sides. And if we just follow it through, we can see that this works as well. So with this, so we start with the diagram. So we start with our diagram, and now the reason I've drawn this green rectangle is to indicate that we're applying this rewrite rule here. We're just applying it to the stuff in here. So that replaces it with this stuff here. And then next, we're going to work on this region that I've drawn this green rectangle on, and we're going to apply this associativity thing here. I suppose it's really sort of, they call it co-associative because it's kind of backwards and it's to do with copy instead of adding, but it's the same kind of idea. So that kind of moves this down here. So now I have this picture, and now we're going to operate on this bit again with the associativity. And now here's an interesting bit because we've created this little bubble here. And so now we can apply this thing that's saying 2 equals 0. And so that's going to make this part of the diagram disappear. So we have this, and then we can use these sort of unit style rules or the swapped round versions of those to kind of heal these little bits, and then we end up with this. So it's saying that x and y come in, we copy x, and then we add up there. And so you can see that this is having the same effect as the original diagram. It sends x and y to x plus y and x, although it doesn't involve us having to sort of manually work out that oh, 2 is 0, so let's get rid of this part of the expression. That's all being performed just by kind of simplifying this expression using the graphical rules. But there's a lot more that one can look at. For example, that if it's a reflection, is it true that if we times it by itself, we get the identity? Well, that's the kind of thing we can check using these rules. Um, there's also, if we do, let's say, this one to itself 3 times, is that gonna, what's the diagram that should go there? And is there a graphical proof that doing it to itself 3 times is going to get the identity? So it really does act like a rotation and all of this kind of stuff. But also, one can go beyond just these particular, you know, these 6 of the 2 by 2 matrices, mod 2. There's more than 6 of them. I think there's 16 of them. And, there's all sorts of interesting structures within those. And, then one can change their finite field that one's working with, or go to higher dimensions, or there's all sorts of um, interesting things that this graphical in your algebra can be applied to. And I'm only scratching the surface as far as you know um, resources and approaches and things. So if you look at that graphical in your algebra blog, it goes into a lot more than I'm talking about here, but it does so from um, a point accessible to anybody. Okay, so as a sort of bonus feature, I just wanted to return to this square, which is working within our ordinary number system. So let's say we're working with rational numbers or real numbers, which are the things that go in these matrices. So we're no longer talking about this mod 2 case. We're returning to the case where let's say we're working with matrix 2 by 2 matrices of integers. And we were discussing before how these different matrices corresponded with these different symmetries of the square, and also with these different sort of diagrams, which we can call signal flow graphs or string diagrams. Um, However, there's an operation that we really like to do in situations like this, because as I've discussed in other videos on the two by two matrices, if we have, let's just say real numbers, let's be conventional. So A and B are real numbers, and we have A plus B times I, or better to say it like this. Let's call this matrix here, this identity matrix, 1. So A times 1 plus B times I. So unpacking this a little bit, we've got A, and then this identity matrix plus B, and then this matrix up here. Okay, and then it turns out that this behaves just like a complex number should behave. So this is a really nice connection where, you don't have to sort of fantasize about there being a square root of -1. In the world of two by two matrices, we have such a thing, and we call it I. Um, Now, in order to actually be able to do this, though, what do we do in graphical linear algebra? Um, well, one thing which I think is kind of cool is, let's think of this A as a sort of scalar. So we can maybe draw it like this. So an input X comes in, and then A times X comes out. So within the framework that we've already been talking about, we've encountered this situation, which basically multiplies the input. I should have used purple. Um, it multiplies it by 2. So this is kind of like thing that multiplies by 2. And indeed, we can have this kind of graphic. So, you know, if we want to compose. So for example, if we want to compute what this matrix is, okay, so I think one way we can look at this is, let's make up a matrix. We'll call it A tilde, and it's this matrix here. B tilde is like this. And then the point is that for xy, if we have some matrix, like let's say this one, it could be any matrix, and then we want to times that by b, then we could sort of equivalently work out this. And that's going to be equal. But we could also write that like this. And so that's our matrix after this B tilde thing. And so this B tilde thing is going to look like this. And we do that first, and then we do this I matrix thing here. So what we swap first, and then we've got a minus on the top. So that would be an example of scaling a matrix. But then how do we add how do we add these two things? So what I've tried to do here is sort of graphically compute. So I got the diagram from here, and then I appended, let's say prepended um, that multiplied by b. Also, we can get this identity diagram here and prepend multiplication by a. That gives us the other thing that we want to add together. So that's going to be this. And that's going to be equal to A times the identity matrix. And then the next thing we have to do is to add these two things together, right? Because this is A times 1. And this thing here is B times I. And what we wanted to compute is A1 plus BI. And now the way that we can do this is we get A1 and we put that at the top. And then we get BI, which is here. And you can do a similar procedure using any initial matrices, but yeah, so we put BI there. And now what we want to do is sort of fuse these wires. So the top one adds to the top one, the second one adds to the second one. And that's the result. And our input comes in here. We have a couple of copy. And so this top channel gets an X and a Y, and this bottom channel gets an X and a Y. So that's how we add these matrices. So let's see how this works. We feed in X and Y, and then we get X here, Y here. And now we get AX and AY. Minus BY BX. And so the result is AX minus BY BX plus AY. So now let's work this out in the normal way. So what we're talking about here is this matrix M, call it like this. And now what we just computed would be M operating on X, Y, which is going to be this, which is going to be AX minus BY BX plus AY. So yeah, that makes sense. So you see now how we can also add matrices in this framework and scale them. So it's a really rich arena to study these different matrix groups. And I think, you know, now we have a way of looking at it with this sort of high dimensional geometry. Maybe there's some other questions we could think about, like, you know, um, playing around with these different rewrite schemes, for example. Or I mean, it sort of for me this is drawing me into this graphical linear algebra blog more because it's very deep, especially when it gets into this category of linear relations as well. And it seems like there's opportunity to look at a lot of sort of exceptional structures in maths and things, which are normally studied with linear algebra, and to think about how they manifest in terms of this category of linear relations where there's more going on. And I think that's an exciting prospect. I think there's lots of exciting things about, you know, also just delving into the way that fractions get treated in this category of linear relations and the sort of number theoretic connections.